Welcome to the next lectures of ongoing course on perception system, perception algorithms. So, we took an example of radar tracking, 2D radar tracking in my last lecture. This thing we will take a bearing angle only tracking problem. With this here is the problem. You see, this is actually say a very interesting problem. A platform in a plane moving in a 2D using some discrete equation. So, your x and y, this is actually your truth motion, So, x is actually this is x bar and this is error in x. Y it is y bar and this is y bar in y. Okay. Now, x bar p, y bar p are average platform coordination and this is the perturbation. So, this is your process noise you can roughly qualify and they have say certain variance with 1 say meter. Okay. So, and this is governed by this equation. So, your mean value for x direction is a linearly increasing function 4 into k and y value it is actually say constant say 20. Okay. And this is your target true equation, target true state. So, and time t you can assume as 1 second. So, with this you get 1 t, t is 1. So, 1 x k plus t square by 2 1. So, 1 by 2 1 v k or your process noise. Okay. Do not mix it here, it is in terminology as v k, but it could be w k, it does not matter. x1 x2 position velocity of your target, right. Let me go to the next thing. Now, you have a sensor. Okay. Sensor is giving you line of sight angles. These are your line of sight angles. This is your line of sight angle, this is your line of sight angle. Okay. Z0 and say after t equal to 20 samples, it is giving you another thing. It is just a your h function. So, tan inverse y by x, obviously you can see it from your geometry, you can see it from this is your measurement. So, tan inverse y by x, okay. Y is this yp, because yp I have taken is 20 constant, x1 minus x1p. So, it is one dimensionally this plane, this ball or whatever you say, this point is moving from one place to another. Now, you assume that here your measurement error is kind of corrupted with say Gaussian variance with 3 degree standard deviation plus your initial condition is x0 is like this and obviously you can have your process noise variance, they have assumed something 0.01. Now, we will be applying here estimated target state we need to find out from this sensor measurement and we will deploy here first we will be deploying here EKF extended Kalman filter, second we will deploy here pseudo measurement filter. EKF is straight away we will deploy it and then we will deploy pseudo measurement filter and we will see the performance, how actually they work. This is my measurement function. Okay. Now, what is there? xp and yp is there. xp, yp itself is changing, xp is 4k, yp is 20 and all something value is there. So, I need to take when I take the total this measurement error, the angle measurement error, I have to along with this measurement noise, I have to add this term as well, because this measurement function is changing with respect to xp, measurement function is changing with respect to yp. Well, yp is constant, I do not care much, but you have to take it because xp and yp I have think this is kind of a variable, because xp I have assumed say 20k or something, some function of k, what is the value 4k is 4k, yp is equal to 20. So, I have to take the variation of delta h versus delta x p and a delta h versus delta yp, both variation I have to cater. With this, if I calculate the measurement error variance, I get something like this kind of expression. It is easy to calculate. So, your actually measurement error, say z tilde I am telling, it will be del h by del xp into delta xp, del h by del yp, delta yp plus Ws, expectation value 0, take expectation 0. Now, delta h by delta x you do derivative, delta x by delta h by delta y you do derivative, and then take the square, simple square. So, expectation of x p square, expectation of y p square, expectation of W s square. So, that values will come into here, and when you do, you will get something like this. Okay. So, omega is directly R s, but the rest are all same. So, you get, so your the thing is that now your variance, the problem is like this. So, your measurement error variance is kind of a linearly increasing, and sometimes it is constant, sometimes it is increasing like this. Okay. So, this is what is happening. Okay. Now, what I will do, I won't go for directly a pseudo-linear filter. So, I will first implement an EKF, and then perhaps I will go a pseudo-linear filter. Okay. So, first part is obviously my filter initialization. In any Kalman filter, whatever I do, I have to initialize the filter properly. If I do not do initialization properly, there will be certain error in it. So, how to do the initialization? You can again look into this equation. This is your angle. Angle is say this angle h dot, I am assuming it is a theta. Okay. So, when you do this, you get actually this equation. Just do a simple. So, I am just telling you how to do it. Eta equal to tan inverse, yeah. Say eta is equal to tan inverse y p y bar p divided by x 1 minus x bar p. So, now you can do it tan of theta, eta actually, y bar p equal to x 1 minus x this bar. Okay. So, x now will be obviously x p plus y bar p divided by tan of eta. Now, once you get it, so this is actually x 1 is your position, you get it. So, now you differentiate, you get x 2, simple 2-point differentiation, and now you calculate your P 11 and P 22. Obviously, P 11, P 22 is very easy, actually x 1 this thing plus this. So, P 11 if you can calculate, then you can calculate P 22. How to calculate P 11? Again you do a first order Taylor series, calculate the Jacobian with respect to x p y p. That is all I have done here. And obviously, delta z is there, that is the measurement error. You take the thing and you start doing the error calculation. So, delta z is the error in angle measurement, W s 0, whatever thing, platform perturbation. So, your x 1 0 is coming like this. Now, if you take simple x, just this is simple Taylor series linearization. Okay. If you take expectation of this is 0, this is your mean. Now, variance how to calculate? Expectation of delta x p square 1 by tan squared z, just you do square into expectation of delta y p square plus y p bar square divided by sin square z, expectation of z square, delta z square. This is actually your R x, 1 meter perturbation given 1 by tan square into z, z eta both are same, R y 1 meter again, y p bar square sin to the power 4 z into R s. So, this is going to be the variance of x 1, or this is actually your P 11. Once you find it out, you can find out now P 22. Okay. With this now we try to implement an EKF. EKF what we do? I already told EKF. EKF actually you have to linearize your measurement, because your state model is linear, measurement model is non-linear. So, we have to do that. Okay. How to do that? State prediction done, 1 t 01 you have done, covariance error prediction you have done, measurement matrix again you are doing some linearization of your tan inverse component. So, this is your measurement, guys, this is your measurement. What is this is your measurement. EKF has to take the full measurement actually. Okay. This is your measurement. This you have to linearize. How you linearize? Again, you have to calculate what is known as your first order Taylor series linearization along with your x. So, first will be del h divided by del x, okay, and del h divided by del x dot, right. With respect to your state, you have to do linearization. Once you do this, x dot anyway no term is there, so it will be 0. Once you do with x, you will get this term. Okay. You calculate your measurement residual, because you are now using the nonlinear measurement. So, with nonlinear measurement minus nonlinear predicted measurement minus the nonlinear actual measurement. So, actual measurement minus predicted measurement, you get the measurement error residual. Okay. Already you have calculated your R matrix from this problem. You have calculated already your R matrix. This is your R matrix. You have already calculated. So, take this expression here. You calculate this. Rest are all Kalman filter equation. Your predicted measurement error covariance, gain computation, updated state error covariance, just a standard Kalman filter equation. So, with this you can implement an EKF. Now, there are two things I would like to tell. Why this problem is chosen? This problem is chosen because of two reasons. First, this will help us to understand the mean and covariance calculation of a stochastic signal. Because of this problem is particularly chosen, if you have see here, your platform motion, you have seen the average motion is also time dependent I have made. Okay. So, the definitely your state, this total, when you say the process noise, it is going to be changing. Your measurement noise, you have seen that it is also another component. So, when you take the total measurement component, because of the variation of xp and yp, your total measurement error component is going to change. That is what we have seen in here in this expression calculation. So, that is why you have seen this, because of variation of xp, variation of yp, your h is changing. So, in a state, when you are doing the error covariance calculation, you need to remember what are your dependent variables that are changing. With that change in the dependent variables, how your measurement function is actually changing, because here my xp yp is changing, they are not constant. X and y is there, but xp yp is my platform mean motion, they are changing. So, obviously my angles will change. So, I have to take that impact into my measurement error variance calculation. That is why this problem is chosen. This is a bit difficult problem, but but there are a lot of things we can learn it from this particular problem. And when I will show, obviously in the next class, when I will implement the PMF or the pseudo measurement filter, then a very typical example thing you will be finding out. Okay. So, with this now I go to my EKF section again. So, with this EKF, and before that I would like to tell again this error calculation by initialization calculation. EKF, sometimes it is initialization dependent, not all the time, but sometime, very few, but very minimal, sometimes it is initialization dependent. So, here we have used simply 2-point extrapolation principle, 2-point extrapolation principle. So, my position I have used my first measurement, and the derivative of that I get my next state, and I get my P22 as well, and error in the initial position estimate I get it like this. So, again xp is changing, yp is changing. So, this thing will be total, this g function will be totally changing, okay, and delta z anyway is a changed quantity itself. So, that is why I have calculated this thing like this and P0 like this, okay, and I have implemented my EKF. So, EKF is simple. Again, I have used my nonlinear measurement. I have not done any linearization the way I was doing for pseudo-linear filter. Here I have taken my nonlinear measurement and nonlinear predicted measurement and the nonlinear measurement itself. Only thing I did my measurement matrix linearization just to calculate my Kalman gain or my output error covariance, whatever you say. So, H matrix I have calculated it del H by del X, del H by del X dot, I get this expression. Okay. and with this now total EKF is built. EKF is built. Now, you will see a typical thing. Now, there are too much nonlinearity into this thing that you are assuming, because I am, first of all, the system is not observable fully. If it is range and if it is angle, it is fully observable. Plus, but here it is actually a 1D measurement. Okay, you have only yp, but x1, at least you can estimate it, but degree of observability is little bit lesser. If you have another equation, say eta dot, observability would have been more. Why? What I am trying to tell again and again by taking time is that there is also a direct connection in Kalman filter or EKF divergence or EKF convergence, because EKF is a approximation method. It is a first order Taylor series approximation within the mean of Gaussian random variable. It disregards the probabilistic spread of the system. Okay. So, having said so, now any EKF, if you see, it is only x1. To some extent I can estimate it, but my x1 measurement is not very accurate, because I do not have any range and all. Okay. So, with this, actually this example, I am telling you the result, EKF will diverge, but pseudo measurement will converge. That is why this particular expression example is chosen. So, with this now, and this is a first order EKF, obviously first order Taylor series generation. So, here you can see my H is del H by del X dot. I am doing again a summary how to implement the EKF, because I do not will not go to pseudo measurement in this lecture. We will do it in next lecture for the same problem, how to implement pseudo measurement. So, EKF, I have state prediction x f of x k, okay. Covariance matrix prediction, simple Kalman filter I have done. Then I have done a linearization of measurement matrix del H by del X dot. I got measurement matrix like this. Okay. I calculate actual measurement minus predicted measurement, predicted non-linear measurement, I got it like this. Okay. Then I calculate my measurement noise variance. Measurement noise variance is not a converted measurement noise variance, which I was doing for pseudo-linear filter. It is a different kind of a, it is actually the system is like that. I have to calculate this. You have seen this expression. Because of variation, my XP, platform motion variation, XP and YP, I have to take the variation of XP, YP into account to calculate the bearing angles. So, that is why my R matrix is changing, because if I take my R is only WS, change in WS, it is wrong, because my XP, YP both are changing. So, that is why I have to recalculate my R. Well, it is actually giving me this thing, fine, no issue, but that is why I have done it with a mean point. Mean is your XP bar, XYP bar, plus the first order variation I have taken to calculate my statistics R. So, I got this kind of a term, okay, and I have plotted it here also, actually how the noise variable is varying. You can see it is constant, it is not constant, it is kind of a monotonically increasing, okay. And that is why now you get equivalent measurement error covariance matrix is like this. So, now you get all the things here. So, this example is important, we will be now implementing, and we implemented extended Kalman filter. In this thing we will implement a pseudo-linear Kalman filter. The same problem, if you remember, this is your problem. So, your X platform is moving with a linearly with a certain time, and YP bar is kind of held constant. With this we implemented EKF last time. Now, we will implement the PMF. PMF is pseudo-linear, pseudo measurement filter. Measurement equation. Now, let us calculate a pseudo measurement. Pseudo measurement means which is not an actual measurement, which is a fictitious measurement. That is why the name is pseudo measurement. Previous time we have calculated it, okay, Cartesian measurement we have converted from polar, or from cylindrical we converted to Cartesian, because my state is in Cartesian, I get linear. But here actually what I will do, I will calculate a fictitious measurement. What is a fictitious measurement? That measurement actually does not exist, does not give by my sensor, but by algebraic manipulation I am calculating or defining a kind of measurement which will make my filter linear. How to do that? Here you see tan inverse function is there, or definitely it is non-linear function. So, with this non-linear function now I will be changing it. I don't just I am doing it like this. Tan of eta yp divided by x1 minus xp. Now, I can write it x1 equal to say xp plus yp by tan of eta. I can write it very easily, I can write it, not a problem, but I will do it in different way. I write it sin of eta by cos of eta yp divided by x1 minus xp. Okay. So, yp cos of eta is equal to x1 minus xp into of sin of eta. Now, I take this thing. So, x1 minus xp sin of eta minus yp cos of eta equal to 0. This I am assuming a pseudo measurement. There is a reason for it. There is a reason for it. Why I have chosen like this? The reason is, actually if I choose it like this, then actually there is no noise. You can assume, because difference is 0. So, actually there is no noise. That is the reason we call it noise free pseudo measurement. I am doing tan into sin by algebraic manipulation. I have put it like this way, so that you actually do not have anything, your sin theta and cos theta. You calculate your predicted measurements, okay, fine. Predicted measurement means now actually it is 0, it is 0. That is the best advantage for me. So, actually so you see, when you am calculating the residual, I am subtracting from 0, because this value is 0. What is there? Your residual is actual measurement minus predicted measurement. Now, actual measurement actually is 0, because I have algebraically manipulated it to make it 0, to enforce it to be 0. So, I do not need any physical measurement, although I need it to calculate these things, but actually here actual measurement actually will be 0. So, that is why it is called noise free pseudo measurement. So, 0 minus predicted measurement, x1 minus xp hat sin eta m yp this thing. So, you get it like this. Okay. This is a simple expression, simple this thing. Once I get my innovation error covariance, innovation error, I have to calculate its statistics. So, what is my mean? Mean is 0, obviously I do not care about mean. Okay. When I do my covariance estimation, I get it some expression like this, same Taylor series, squaring and all like this. There is nothing new here. So, actually how? This is my error. You can yourself calculate some algebra, do a square, your cross terms will vanish. So, when you do the square, you are actually getting it, see you are doing square. So, a plus b whole square kind of a formula. So, you can just yourself calculate expectation of this minus this into this expectation plus this plus this. You can yourself calculate it, you can get some expression like this of your innovation error covariance. Anyway, that is not very important for you. For you is important is your R matrix calculation. Again, I am telling. Once you have done this, so this is actually your H matrix, because you have to write it as H into X. Okay, not H a function of X, you have to write it H into X. So, you get H matrix is like this. With this, now your R matrix becomes this, some equation, and your CPMF implementation, I get a linear H matrix. That is why I have done 0, that means noise free measurement, because my measurement is 0. So, H is like this, I get my measurement residual is like this, and my R is updated with this. Obviously, with M I have to replace it with prediction. Once I do this, this is very important. I now simulate it using both filter, my EKF plus as well as my pseudo-linear filter. First I do a 100 run Monte Carlo. Once I do the 100 run Monte Carlo, I see, well, EKF is the form line is EKF, others are actually pseudo measurement. There is also a particle filter is there, forget particle filter, not required for this lecture series. Mota they are same, not a difference. Velocity error also not so great, I would say they are not converging actually in this thing. Position at least is converging, but velocity error, well, it is kind of, it can go to negative also, it is not very much converging, not very good, but at least it is okay, it is not diverging at least. Now, I took 1000 run Monte Carlo, that is why this problem is chosen. particular problem, very different problem, bearing angle diagram problem. So, here you see now EKF diverge. In one run EKF diverge. So, you have seen here EKF gone high, EKF has gone high. Okay. So, that means that is why nonlinear filter convergence has to be tested using a Monte Carlo simulation, not using any single run. Will not be able to tell you whether that is why this problem was chosen, whether this thing is actually your EKF is converging or not, but you see your pseudo linear filter is converging. Now, why it is so? Why it is so? That I will tell in next lecture in detail. I will again revisit this thing. So, but this is the reason. This is the reason your actually EKF is getting diverged. In one run, if it is diverged, the RMS error will fully blow up, and that is the problem. So, with this, I would like to say thank you for this lecture session. In the coming lecture, we will continue with this problem once again. I will again explain the pseudo measurement filter once again, so that these calculations and all at least you understand, and then I will tell you the reason why EKF is diverging. Thank you for your time. Thanks.